March 17, 1943, show 9 to 14 a.m. Luftwaffe Technical Intelligence Center, Rechlin, Germany. The Wright R-1820 Cyclone engine sits on the examination table like a dissected beast, oil-stained and battle-scarred. Oberingenieur Klaus Hoffman circles it slowly, notebook in hand. His team of 6 engineers waiting behind him. The engine was pulled from a B-17F that crash-landed near Bremen 2 weeks prior. The 4th Flying Fortress captured intact in 3 months. Hoffman's orders are clear. Identify vulnerabilities, assess production quality, determine why these American bombers keep making it home despite catastrophic damage. The Luftwaffe has logged 847 sorties against B-17 formations since January. Expected kill rate, 12%. Actual, 4.7%. Begin documentation, Hoffman says quietly. His wrench catches morning light through the hangar window. What they find will change nothing about the war's trajectory, but it will explain everything about American engineering philosophy and why the Flying Fortress earned its name. March 17, 1943, 09:30 a.m., Rechlin Technical Center. The engine's external housing shows 43 impact points, flak fragments, cannon strikes, one clear .30 caliber entry wound that somehow missed every critical system. Hoffman photographs each mark methodically. His assistant, Lieutenant Werner Brecht, transcribes observations in careful script. Cooling fins intact despite frontal damage, Brecht notes. Oil reservoir shows emergency patch. Field repair. Crude, but functional. Hoffman nods. He's examined 11 Allied engines this year. British Merlins are elegant, precisely toleranced. This American radial is different. Heavier, over-engineered, almost brutish in its construction. He traces a finger along the cylinder head. The metal is warm despite sitting cold for days, as if retaining memory of flight. Outside, a Focke-Wulf FW-190 roars past on takeoff. The sound rattles the hangar's thin walls. Hoffman's team doesn't flinch. They've learned to work through noise. Remove the cowling assembly, Hoffman instructs. I want to see the accessory drive section. 3 men lift the engine's outer shell. Afternoon light floods the internal mechanisms, a maze of push rods, rocker arms, and intercylinder baffling. Everything is larger than necessary, Hoffman notes. Overbuilt. The Germans chase efficiency through precision. The Americans achieve reliability through mass. Brecht leans closer. Look at the magneto mounting. Double redundancy. Photograph it. The Leica shutter clicks 5 times. Each image will be analyzed in Berlin, compiled into reports that flow upward through Luftwaffe intelligence channels. Somewhere in those reports, patterns will emerge. But patterns won't stop the bomber streams now crossing into German airspace with increasing frequency. Hoffman pulls a small notebook from his pocket, his personal log, not the official documentation. He writes, engine shows operational damage consistent with Category 3, combat encounter. Continued function despite compromised cooling systems suggests design tolerance exceeds tactical assessment parameters. He doesn't write what he's thinking. This engine was built by people who understood their crews would be alone over hostile territory, hundreds of miles from help, with no option but to keep flying. March 17, 1943, 11:00 a.m. Rechlin. Hoffman's team removes the supercharger assembly, a complex mechanism that forces pressurized air into the cylinders at high altitude. The unit weighs 43 kilograms. German superchargers achieve similar output at 31 kilograms. Wasteful, says Oberfeldwebel Hans Krieger, the team's senior mechanic. He's 52, trained in Munich's technical institutes before the war. Why carry the extra weight? Hoffman examines the unit's internal gearing. Look at the tooth wear pattern. Minimal degradation after... He checks the engine log card, still attached to the mounting bracket. after 8:47 flight hours. The German engineers exchange glances. Luftwaffe engines are rated for 500-hour intervals between major overhaul. This American engine has been flying combat missions for nearly a year. Brecht photographs the supercharger from 6 angles. The gear teeth are wider than our specifications. Tolerances are looser. You can see the play in the mesh. Loose tolerances mean the parts don't seize under thermal stress, Hoffman observes. Precision fails at temperature extremes. This design accepts imperfection to maintain function. It's a philosophical difference, he realizes. German engineering pursues the theoretical ideal, perfect fit, maximum efficiency. American engineering accommodates reality, thermal expansion, vibration, damage, fear. Outside the hangar, air raid sirens begin their low wail, not an alert, just a test. The sound fades after 30 seconds. Hoffman's hands never stop moving. He disassembles the fuel injection system, laying each component on a clean cloth in sequence. The injector nozzles are brass, not steel, softer metal, easier to replace. Each nozzle is stamped with a date code and factory identifier. Wright AER, Corp, Pattern, NJ, 1142. November 1942, 4 months from factory to combat to capture. The American production tempo is staggering. This entire engine, Hoffman says slowly, is designed for replacement, not repair. Every major component has quick disconnect fittings. A trained crew could swap this complete power plant in under 4 hours. Krieger frowns. That's impossible. It takes us 3 days to replace a BMW 801. It's not impossible if you're building 1,500 aircraft per month. Hoffman straightens, his back aching. They're not trying to make perfect engines. They're making 10,000 adequate ones. March 17, 1943, 02:15 p.m. Rechlin. Lunch was black bread and ersatz coffee. The team returns to find the engine partially disassembled by junior technicians, cylinder heads removed, pistons exposed. Hoffman inspects the combustion chambers. Carbon scoring is minimal despite the flight hours. The piston rings show even wear. American metallurgy is excellent, he admits to Brecht. Whatever alloy this is, it resists thermal breakdown. Brecht measures piston diameters with calipers, within tolerance, barely, but functional. The afternoon light shifts, streaming through high windows. Dust motes drift in the beams. Somewhere in the building, a radio plays Beethoven, the 7th Symphony, second movement. Hoffman finds it inappropriate. This work requires concentration, not emotion. He turns to the engine's ignition system, twin magnetos that generate spark, independent of external power. Each magneto can operate alone if the other fails. Redundancy again. The wiring harness is thick, almost clumsy, with multiple shielding layers. They're protecting against battle damage, Hoffman says. A single bullet might sever one circuit, but the secondary paths remain functional. Krieger holds up a severed wire from the captured engine. This one was cut, clean shear from shrapnel, but look, he points to a crude splice, wrapped in electrical tape. Field repair, probably done in flight. Hoffman imagines it. A crew chief or engineer in the bomber's cramped fuselage, wind screaming through torn metal, fingers numb with cold at 20,000 feet, making emergency repairs while fighters circle and flak bursts bloom black against the sky, making repairs because there is no alternative, because the mission clock is running and the target is still ahead and home is 3 hours away across an ocean. The German engineer has never flown in combat. He's 41, too old for aircrew service, classified as essential technical personnel, but he reads the mission reports. He knows what happens in the sky above him. Continue documentation, he says. I want metallurgical samples from each cylinder, Send them to the testing lab in Berlin with priority designation. Brecht makes the note. The paperwork will take 3 days to process. The samples will take 2 weeks to analyze. The reports will circulate through intelligence channels for months. By then, the war will have moved forward, and this engine will be obsolete data. But today, it's evidence of something Hoffman is beginning to understand. The Americans are building machines that accept damage as inevitable and continue functioning anyway. March 18, 1943, 080 AM, Rechlin. The second day begins with the engine completely disassembled. 67 major components spread across 4 examination tables, each piece tagged, photographed, measured. Hoffman arrives early before his team. He walks among the parts slowly, noting details. The crankshaft is massive. Over-engineered again, he thinks. But the bearing surfaces are mirror smooth despite the wear hours. The connecting rods are forged, not cast. Stronger, more expensive. The Americans can afford the expense. Brecht enters carrying a folder thick with overnight observations. The fuel system analysis is complete. They're running 100-octane aviation gasoline, higher rating than our 87-octane standard. Higher octane allows higher compression ratios, Hoffman says, more power from the same displacement. But where are they getting the refining capacity? Hoffman doesn't answer. The question is rhetorical. American industrial capacity is a mystery the Third Reich has consistently underestimated. Intelligence reports suggest 50,000 aircraft produced in 1942 alone. The number seems impossible, yet the bomber streams keep growing. He picks up a pushrod, a simple component, just a steel tube with hardened ends. It weighs 190 grams. The German equivalent weighs 140 grams. 50 grams multiplied by 18 pushrods multiplied by 4 engines equals 14 kilograms of unnecessary weight per aircraft. But this pushrod survived a direct hit that shattered the rocker arm it connected to. The American part bent, but didn't fracture. The lighter German design would have failed completely, triggering catastrophic valve timing failure. They're building in failure margins, Hoffman says aloud. Krieger looks up from the valve train assembly. Pardon? Every component has excess capacity. The engine can lose 30% functionality and still operate. A German engine at 70% capacity would seize. That's inefficient. That's survival. The distinction matters. Efficiency wins in peacetime. Survival wins in war. March 18, 1943, 11:30 AM, Rechlin. A courier arrives with a classified folder, operational intelligence from Luftwaffe Fighter Command. Hoffman signs for it, dismisses the courier, reads alone in his office. The report details a B-17 engagement over Wilhelmshaven on March 12th. A fortress from the 91st Bomb Group took 73 confirmed hits. Cannon and machine gun fire. The bomber lost 2 engines completely, 1 caught fire, the electrical system failed. Tail gunner killed, waist gunner critically wounded. The aircraft flew 280 kilometers back to England and landed successfully. Hoffman reads the fighter pilot's account. Target bomber displayed catastrophic damage, expected immediate loss of altitude and structural failure. Bomber maintained formation and returned effective defensive fire, disengaged after ammunition expenditure. He sets the report down carefully. 73 hits, 2 dead engines, still flying. He returns to the hangar, where his team is examining the oil lubrication system. The pump is larger than necessary, redundant capacity again. The oil reservoir holds 18 litres, with emergency backup tanks adding another 9. If they lose oil pressure, these backup systems engage automatically, Brecht explains. The engine can run for 45 minutes on reserve lubrication alone. 45 minutes. Enough time to reach the coast, enough time to cross the channel, enough time to bring 10 men home. Hoffman thinks about the German bombers, Heinkel, He-111s, Junkers, Ju-88s, that have been flying night missions over England for 3 years. Their engines are excellent, precise, efficient, but when they fail completely. How long can our engines operate with compromised oil pressure? He asks Krieger. The senior mechanic considers. 8 to 12 minutes before thermal seizure. 1/4 the American endurance. The difference between reaching safety and dying in the North Sea. Hoffman makes another note in his personal log. Operational philosophy prioritizes crew survival over engineering elegance. Mission completion rates reflect this priority. March 18, 1943, 02:45 p.m., Rechlin. The propeller hub arrives from storage, a 3-bladed Hamilton Standard constant speed unit weighing 180 kilograms. The team needs a crane to position it on the examination stand. Hoffman inspects the blade pitch mechanism. It's hydraulically actuated with mechanical backup. If hydraulics fail, springs return the blades to a coarse pitch setting, less efficient but functional. Another failure accommodation. The whole design philosophy assumes battle damage, Brecht observes. Nothing is allowed to be a single point of failure. Because single points of failure kill crews, Hoffman replies. He's thinking about his son, Luftwaffe pilot, flying Bf-109s over the Mediterranean, 23 years old, 12 combat missions. His letters are cheerful, vague about danger. Mothers don't need details, he writes, but Hoffman reads the casualty lists. He knows the numbers. He knows that German fighters are excellent machines, but when they're hit, when fuel lines rupture or coolant systems fail, pilots have minutes to find somewhere to land. Often they don't find it. The B-17 crews have options. They can shut down engines. They can limp home on 2 power plants out of 4. They can absorb damage and keep flying. His son's fighter has 1 engine, 1 pilot, 1 chance. Hoffman shakes off the thought. Professional detachment is necessary. This is technical analysis, not personal reflection. He examines the propeller blade root, the point where blade meets hub. The attachment is mechanical, not welded. If a blade is damaged, it can be replaced individually. German propellers are integrated units. 1 broken blade means replacing the entire assembly. Parts interchangeability, Krieger notes. Every component is standardized. Any B-17 can accept parts from any other B-17. Logistics, Hoffman agrees. They're thinking 3,000 kilometers beyond the factory floor. They're designing for field maintenance in primitive conditions. Outside, the afternoon fades toward evening. The hangar grows colder. The team works in silence, measuring, photographing, documenting. March 19, 1943, 09 Koisil AM, Rechlin. The third day focuses on the engine's electrical systems. Hoffman and Brecht map the wiring harness, each circuit, each connection point, each backup pathway. The schematic grows complex. Dual generators, dual voltage regulators, 3 separate battery systems. If the main generator fails, the auxiliary unit engages. If both generators fail, batteries provide 40 minutes of essential power. 40 minutes again, Brecht notes. That number keeps appearing. Time to cross the channel, Hoffman says. They've calculated minimum survival endurance and built every system to meet it. The wiring itself is over-insulated, thick rubber sheathing that adds weight but resists damage. Hoffman cuts a sample with wire cutters. The insulation is 3 millimeters thick. German standard is 1.5 millimeters. Fire resistance, Krieger suggests. If fuel ignites, these wires won't short immediately. Hoffman tests the theory with a flame. The insulation chars but doesn't melt, doesn't expose the conductor. Fire suppression through material selection, simple. Effective, heavy. A knock on the hangar door. A Luftwaffe major enters, tall, thin, wearing the Knight's Cross at his throat. Hoffman recognizes him from photographs. Major Wilhelm Schneider, fighter ace. 37 confirmed kills. Oberingenieur Hoffman. The major's voice is formal, clipped. I'm here to provide operational context for your assessment. Hoffman wipes his hands on a cloth. Major, please. They walk among the dissected engine parts. Schneider examines them with professional interest, hands clasped behind his back. I've engaged these fortresses 9 times, Schneider says. Shot down 3, damaged at least 12 others. They're difficult targets. Why? They absorb punishment. I've put cannon rounds into engines and watched them keep running. I've set fires that should destroy the aircraft. They extinguish them somehow and continue. The defensive firepower is extraordinary, and they fly in formations that create overlapping fields of fire. Hoffman shows him the oil system. This design allows 45 minutes of operation after oil pressure loss. Schneider nods slowly. That explains several incidents. Bombers I was certain would fall didn't. Your tactics assume mechanical vulnerabilities that don't exist. Apparently so. March 19th, 1943, 02 Saug PM, Rechlin. Major Schneider stays for the afternoon session. Hoffman appreciates the pilot's perspective, operational reality matching technical findings. They examine the engine's carburetor, a complex unit with multiple stages. Schneider points to scoring on the throttle plate. Battle damage? Foreign object ingestion, Hoffman corrects. Probably metal fragments from nearby flak burst. The engine kept running despite internal contamination. How? The cylinders are slightly oversized. Small particles pass through without jamming the piston rings. It's intentional tolerance, accommodation for debris. Schneider looks genuinely impressed. They're designing for combat conditions, not laboratory testing. Exactly. Brecht brings coffee. Real coffee, not ersatz. A luxury saved for important visitors, Schneider accepts gratefully. Your report will go to Berlin? He asks. Eventually, through proper channels. And what will you conclude? Hoffman considers carefully. I'll conclude that American engineering philosophy accepts imperfection and compensates through redundancy. That their production capacity allows them to overbuild every component. That they value crew survival over mechanical efficiency. And that our current tactical doctrine underestimates the B-17's damage tolerance. Will that change anything? No, but it will explain why our kill rates are lower than projected. Schneider drinks his coffee slowly. I've lost 4 wingmen this year. Good pilots. They press attacks until the fortress's defensive fire becomes overwhelming. We're told the bombers are vulnerable. We're told concentrated cannon fire will bring them down quickly. He pauses. That's not what I see in combat. Hoffman has no response. Technical analysis can't change tactical reality. The bombers will keep coming, and German fighters will keep engaging them, and men on both sides will keep dying. But maybe, better intelligence can reduce the dying. If fighter pilots understand the B-17's true capabilities, they can adjust their approach, disengage earlier, choose better attack angles, survive longer. I'll include operational recommendations in my report, Hoffman says. Your observations will be valuable. Schneider nods. Thank you, Oberingenieur. After the major leaves, Hoffman writes late into the evening, filling pages with observations, measurements, conclusions. The engine sits partially reassembled on its stand, a monument to American industrial pragmatism. March 20th, 1943, 10 a.m., Rechlin. The fourth day brings unexpected discovery. Krieger is examining the engine mount points, the structural connections between engine and airframe, when he notices something unusual. Hoffman, look at this. The mount points show elongated bolt holes, not circular, but slightly oval. Intentional design. The mounting bolts have rubber damping sleeves that absorb vibration and allow slight movement. The engine can shift position under stress, Krieger explains. If battle damage distorts the airframe, the engine mounts flex rather than fracture. Hoffman photographs the detail from multiple angles. They're designing for airframe damage. The engine can remain functional even if the surrounding structure is compromised. Brecht checks the technical manual. A captured document, partially burned, recovered from the wreckage. Page 47 references shock isolation mounting for combat resilience. It's explicit. They're building flexibility into everything. The three men stand silent, absorbing the implication. German engines are rigidly mounted, precision installation for maximum efficiency. But rigid mounting means any airframe distortion transfers directly to the engine, increasing failure risk. The Americans chose adaptability over precision. Again, Hoffman opens his personal notebook, writes, "Systematic design philosophy emerges. Every component, every system, every connection anticipates damage and provides alternative function paths. This is not accidental. This is intentional engineering doctrine applied across the entire aircraft." He thinks about the broader implications. If the engine reflects this philosophy, the entire aircraft must embody it. The wings, the fuselage, the control systems, all designed to continue functioning despite catastrophic damage. No wonder the bombers keep flying. They're built to expect the worst and survive anyway. A messenger arrives with new intelligence. Yesterday's bombing raid on Bremen. 37 B-17's participated. German fighters and flak claimed 11 aircraft destroyed, but post-battle reconnaissance shows only 4 wrecks on German soil. 7 bombers made it back to England, despite damage categorized as mission kill severity. The numbers don't match. Hoffman has seen this discrepancy in multiple reports. German fighter pilots and flak gunners are accurately reporting damage. But damage doesn't mean destroyed. Not with these aircraft. March 20th, 1943, 02:30 p.m., Rechlin. Hoffman drafts his preliminary report. The technical language feels inadequate for what he's discovered. Not just an engine, but a philosophy. An entire approach to warfare that Germany has failed to understand. He writes, "The Boeing B-17 Flying Fortress represents engineering methodology fundamentally different from European practices. American designers prioritize operational survivability over theoretical performance. Component redundancy, damage tolerance, and field maintainability are integrated into every aspect of the design. This results in aircraft weight penalties of approximately 2,800 kilograms compared to optimized German equivalents, but provides operational endurance that exceeds tactical projections by factors of 200 to 300%. He pauses, rereading. The words sound like excuses, but they're not. They're facts. The Americans accepted weight penalties because they calculated crew survival was worth more than maximum speed. They built heavier aircraft that flew slower, but came home. German designers chased performance metrics, speed, ceiling, efficiency. Different priorities produce different results. Brecht enters with metallurgical analysis from Berlin. The cylinder alloy is chromium-nickel steel with molybdenum additives. Very expensive, but it resists thermal stress better than any material we're currently using. Cost per engine? Estimated 30% higher than BMW 801 production costs. Hoffman does the mathematics. Higher costs, heavier components, redundant systems. Everything about this engine is wasteful by German standards, yet the fortresses keep flying. Maybe waste is relative. Maybe efficiency means different things in different contexts. A lighter engine that fails is less efficient than a heavier engine that survives. He adds to his report, recommend immediate review of Luftwaffe engine reliability standards. Current operational doctrine assumes mechanical vulnerability that Allied designs have mitigated through over-engineering. Fighter tactics should be revised to reflect actual, not theoretical, B-17 combat resilience. Outside, evening settles over Rechlin. The test range falls silent. Somewhere over Germany, bomber streams are forming, preparing for tonight's raids. In England, ground crews are loading bombs, fueling tanks, running engine checks, and those engines, Hoffman now knows, are built to bring the crews home. March 21st, 1943, 08:12 a.m. Rechlin. The final day, Hoffman's team reassembles the engine, a reverse process that takes 6 hours. Every component fits exactly as designed. Despite battle damage, despite 847 flight hours, despite the violent crash that brought this aircraft down, the parts still mesh together with mechanical precision. Krieger torques the cylinder head bolts to specification. Brecht reconnects the fuel lines. Junior technicians reattach the supercharger assembly. The work proceeds methodically. At noon, they complete the reassembly. The engine sits on its test stand, looking almost new. Only the carbon scoring and the patched oil reservoir reveal its history. We could run it, Krieger suggests. Verify functionality. Hoffman considers. They have fuel, compressed air for starting, measurement instruments. But what would they learn? The engine's functionality isn't in question. It survived combat, survived a crash, survived disassembly. Of course it would run. No, Hoffman says. Document final configuration and prepare it for transport to Berlin. The Technical Intelligence Directorate will want to examine it. He takes one last photograph. The complete engine from the front, morning light catching the propeller hub. The image will accompany his report, visual evidence of American industrial capability. Brecht hands him the completed documentation. 127 pages of technical observations, measurements, photographs, and analysis. Hoffman's personal conclusions occupy the final 8 pages. What happens now? Brecht asks. The report goes through channels. Someone in Berlin reads it. Maybe they forward it to aircraft design bureaus. Maybe they file it away. Hoffman's voice is neutral, professional. Our job is documentation, not policy. But he knows the truth. The report won't change anything. Germany can't replicate American production capacity. They can't match the metallurgical quality or the manufacturing tolerances. They can't build engines with 45-minute survival margins because they're struggling to build enough engines at all. The analysis is perfect. The recommendations are sound, and none of it matters. The war will continue on its trajectory, and the bombers will keep coming. And this engine, this remarkable, over-engineered, brutally practical engine, is simply evidence of a gap Germany can't close. April 3rd, 1943, so 3:15 p.m., Luftwaffe Intelligence Directorate, Berlin. Hoffman's report arrives in a grey folder, stamped Classified, Technical Intelligence. It's one of 47 documents processed that week. Major Franz Weber, intelligence analyst, reads it over 2 days. He makes notes in the margins, underlines key passages, flags pages for his superior's review. The technical detail is impressive. The conclusions are disturbing. Quote, "We've been underestimating American engineering capability," he writes in his assessment summary. Current tactical doctrine requires revision. His report goes to Oberst Heinrich Kessler, Director of Aircraft Intelligence. Kessler reads it on April 8th, during a morning filled with crisis updates about fuel shortages and pilot training bottlenecks. File for reference, son, he orders. Forward relevant sections to Fighter Development Command. The report enters the archives. Some sections are extracted for tactical bulletins. Fighter pilots receive updated engagement guidelines. B-17 damage tolerance exceeds previous estimates. Disengage after ammunition expenditure rather than pursuing damaged targets. The guidelines help, marginally. Luftwaffe fighter losses decreased by 3% over the next quarter. 3% fewer pilots killed. Small victories. In Rechlin, Hoffman returns to other assignments. A captured P-47 Thunderbolt needs analysis. A damaged Mosquito bomber awaits examination. The work continues. He receives no feedback on his B-17 report. Official channels rarely provide acknowledgement. But in June, he notices a technical bulletin about engine reliability standards. Several of his recommendations appear, slightly reworded, attributed to, quote, technical intelligence assessment. Close enough. His son returns from the Mediterranean in July, transferred to Reich Air Defense, flying FW-190s against bomber formations. They meet for dinner in Munich. His son is thin, older than 23 should look, but alive. I read an intelligence brief about the Flying Fortress, his son mentions, about their engine design. That was your work, wasn't it? Hoffman nods. It helped. We're more careful now, more selective about engagement angles. Good. They don't discuss the war's trajectory, the shrinking territory, the growing bomber streams. They talk about family, about Munich before the war, about hope for peace. Outside, air raid sirens begin their nightly warning. December 1945, 7 months after victory. Klaus Hoffman, former Oberingenieur, now works in an American-supervised Technical Documentation Center in Munich. The war ended. Germany surrendered. His son survived, barely, flying combat until the final week. An American officer, Captain James Mitchell, requests Hoffman's assistance translating captured German technical reports. The work is strange, helping former enemies understand German engineering for use in post-war aviation development. Mitchell brings a folder of Hoffman's wartime reports. Your analysis of the B-17 engine, it's remarkably thorough. Thank you. I flew B-17's, 35 missions with the 305th Bomb Group, shot up 7 times, always made it home. Mitchell pauses. I didn't know why. I mean, intellectually I knew the aircraft was well built, but reading your report, understanding the engineering philosophy behind every system, that's different. Hoffman nods. The engine was designed by people who understood what combat means. We lost friends, lots of friends, but the aircraft brought most of us through. Mitchell sets down the report. The engineers at Wright Aeronautical, the designers at Boeing, they never flew combat, but they thought about the guys who would. Every redundancy, every backup system, every damage tolerance, someone made conscious decisions about what would keep crews alive. That's what impressed me, Hoffman admits. The systematic integration of survival thinking. German engineering seeks perfection. American engineering seeks reliability. Different philosophies. Different outcomes. Mitchell stands to leave, then turns back. Your son survived? Yes, he's studying engineering at the university now, learning the American methods. Good. The world needs good engineers. After Mitchell leaves, Hoffman reads his old report. Typed pages yellowed with age, photographs fading. The technical details remain accurate. The conclusions remain valid. The Wright R-1820 Cyclone engine was designed to get damaged, keep running, and bring 10 men home. It did that job thousands of times across every theatre of the war. In the end, that's all engineering is, solving problems for people who need solutions. The Americans understood that. They built machines that acknowledged human fragility and compensated for it. Hoffman closes the folder carefully. Outside, Munich rebuilds. Inside, the evidence remains, proof that sometimes the best engineering isn't the lightest or the fastest. Sometimes it's the engineering that brings people home. Hoffman's B-17 engine analysis, dated March 21, 1943, was declassified in 1973. The document resides in the US National Archives, RG 242, Records of the Captured German Documents section. The report influenced post-war American aircraft design philosophy, particularly regarding redundancy and damage tolerance in military aviation systems. The Wright R-1820 Cyclone engine powered over 12,700 B-17 flying fortresses during World War II. Operational records indicate 76% of aircraft damaged in combat missions returned to base successfully, a survival rate that validated the over-engineering philosophy Hoffman documented.